What's good, everybody? Welcome to another video. Hope you're ready to flex those brain muscles, and I hope you're as excited as I am because this is the first video I've made on a calculus topic. So this is really exciting because calculus is freaking awesome. It's a really cool subject, and I got plenty more videos coming. So if you think calculus is freaking awesome too, then go ahead and hit subscribe below. And if you think calculus is really, really freaking awesome, then hit that notification bell too, and you'll be notified every time I upload. So I thought, what better way to start out a calculus series than to talk about limits. This is one of the first things we learn about in calculus. So I thought, okay, I'll do an introduction to limits video. And since this is an introduction, we're focusing on the notation, definitions, a theorem, some basic examples. That's what we're focusing on, the intuition, right? So if you're one of the people, and there's a lot of people out there who are scared of epsilon and delta, there's no need to panic. You will not see epsilon or delta in this video. But my goal is for this video to be a good foundation, right? To help you build the foundation so in a future video, when I pull out the epsilon and delta, you don't panic and you can hopefully understand that precise definition a little bit better. So for now, we're just gonna focus on the intuition, the main idea. What's the big deal with limits, all right? But first things first, we gotta look at notation. So this is how this is read out loud, and you'll have to get very familiar with this. You'll see it a lot. The limit of f of x. The limit of f of x as x approaches a equals L, okay? And here's the intuitive definition. As x approaches a, again, these x values, they're values in the domain, right? We could think of going along the x-axis. So as x approaches a from either side, meaning from the left or from the right, f of x, these are y values, right? Values in the range. F of x approaches L, which is some y value as well, okay? So here's a good example we can look at. The limit of x squared as x approaches 2 equals 4. This is a true statement, and we can visually see that by graphing x squared and looking at what's happening around 2, okay? So if I graph x squared, here's my y-axis, here's the x-axis, and again, I'm only concerned with what's happening around 2, so I don't need to be perfect with this graph, but I'm going to do something like this. I'm going to look at 1, 2. Here's 2. And I could draw a sort of dotted line up. And how do I know what this y value is? Well, I know that it's 4 because when I plug 2 into my function, I get 4. This function is continuous. So it's pretty easy to find that in this case. Okay, so what happens as we approach 2? Let's look at, since it's from either side, let's look at approaching 2 from the left. So I'm approaching 2. My x is getting closer and closer to 2. What's happening to my y values? They're getting closer and closer to 4, all right? From the right, what happens? So now I'm coming from this direction over here. So from the right, as x gets closer and closer to 2, my y's are also getting closer and closer to 4. Let me fix that a little bit. There we go. My y's are also getting closer and closer to 4. So that's why the limit of x squared as x approaches 2 equals 4. Hopefully that's clear to see. And this is a pretty easy example, but one of the reasons why I show this is because I want to point out that we are only concerned with what's happening close to A and what's happening as we approach A, but not what's happening at A. We don't care what's happening at A, right? So what if I erase this and I made it a whole? Let's say I modified this function x squared to where it's undefined at 2. So when I plug 2 into this function, it's undefined. Now what's my limit? Well, let's see. As I approach 2 from the left, my y values are still approaching 4. When I approach 2 from the right, my y values are still approaching 4. So the limit is actually still 4, even though my function is undefined at 2, right? When I plug 2 into my function, it's not defined. So this is kind of the tricky but also kind of cool part of limits, is that we don't care what actually happens at A, right? And it can be undefined, or it can even equal some other number. So what if I now make this a piecewise function? Let's say that's 6 up here, and let's say this is now a piecewise function where I sort of fill in this hole. So when I plug 2 into this function, I get 6, but everything else is still x squared. So it's a piecewise function. Well, now what happens to my limit? As I approach 2 from the left, as my x values get closer and closer to 2 from the left, my y's are still approaching 4, and from the right, the same thing happens as well. So my limit of this piecewise function as x approaches 2 is still 4, even though when I plug 2 into my function, I get out 6. So those are the two sort of tricky things that you'll see. Either the function could be undefined at that point, or it could be defined but equals some other point if it's like a piecewise function, right? So get familiar with those and understand those, but hopefully this helps. Let's go ahead and move on. We'll talk about one-sided limits and a really important theorem. All right, now we got a couple definitions and a really important theorem. Let's go ahead and look at these. So these are called one-sided limits, okay? And this is called our left-sided limit because we're approaching from the left. This one here is called our right-sided limit because we're approaching from the right. And the way I remember this is that when I see that negative up there, I think, okay, we're coming from the negatives, which means we're approaching from the left. And when I see the plus, I think of, okay, we're coming from the positive, so we're approaching from the right. That's just how I personally remember it. So we have our one-sided limits. So let's read our left-handed limit definition. As x approaches a from the left, f of x approaches L. And for our right-handed definition, we have as x approaches a from the right, hence right-handed, right? That's why we call these left and right-handed. As x approaches a from the right, f of x approaches L. So these definitions should look really familiar. It's almost the same as the definition of a limit that we just saw. The only difference is what? This is specifically approaching from the left, and this is specifically approaching from the right. So that kind of logic leads us into this theorem. Because if you remember the definition of a limit, we could approach a from either the left or the right, okay? Either way we approach, we have to be approaching L, right? Our f of x values, our y values have to be approaching L, whether we approach a from the left or from the right. So that logic, again, leads us to this theorem where the limit exists and equals L if and only if the limit from the left exists and equals L, and the limit from the right exists and equals L. So this if and only if means that this goes both ways. So if this is true, then both of these are true. And if both of these are true, then this is true. So they both imply each other. And this is really important to understand, and it's really useful. And how we use it a lot of times is we use it to show that a limit doesn't exist, because we show that the left-hand limit and the right-hand limit don't equal each other. And if we can show that, then we can show that therefore the limit doesn't exist based on this theorem. So it is really important to understand this, and you mostly use this with visual examples, which is kind of the example we'll see in our next example. I'll go ahead and give one, but where you're given the graph of a function, often a crazy looking piecewise function, and you're asked to evaluate and find a bunch of limits. So let's go and look at an example like that. So this is a very common kind of problem to see when you're first learning about limits, is that you'll be given the graph of some crazy piecewise function and asked to find a bunch of limits. So this really tests your knowledge of limits and one-sided limits. So let's go and look at this problem. We have the graph of some piecewise function. F of x is our piecewise function. Can we find these limits? So let's see. The limit as x approaches 2 from the left, right? The minus, I think of we're coming from the negatives. So we're approaching 2 from the left. What are our y values approaching? Remember, these limits over here, these will always be y values. So what are my y's approaching? Well, they're approaching 2, right? As x approaches 2 from the left, y gets closer and closer to 2. So what about from the right? As x gets closer to 2 from the right, my y values are approaching 1. So now we can use that theorem we just learned, right? And we can clearly say that, well, these limits aren't equal, therefore the limit itself does not exist, and we use DNE to denote does not exist. So this kind of example is where that theorem really shines, really becomes very useful, because we can clearly just say it does not exist, right? Let's continue. The limit as x approaches -1 from the left. So as x gets closer and closer to -1, my y values are getting closer to 1. I don't care that there's that single lonely point up there. I'm looking at as x gets closer and closer to -1, what are my y values approaching? Remember, we don't care what's happening at -1, only what's happening as we get closer and closer to it. So my y values are approaching 1 in this case, and it looks like the same thing happens from the right. My y values approach 1. As x gets closer and closer to -1 from the right, my y values approach 1. So that means that this limit does exist and it equals 1, right? So that theorem came in handy again. We could say the limit does exist and equals 1. And I just threw this in here to help y'all see that the limit doesn't have to be the actual output of the function at that value, right? Because when I plug -1 into this function, I get 2. But that's okay, right? Because we don't care what's happening at -1, only what's happening as we get arbitrarily close to it. So hopefully this example helps. Hopefully this makes sense. So if we're asked to find the limit of some function as x approaches some number, just like these examples, if we're asked to find this, how do we do it? Well, this is the first and probably the most important step. And what we do is we always plug a into the function. So the number that x is approaching, we take that and we plug that into the function. if the output, meaning if once we plug this in, whatever number we get out, right? If the output is a real number, then that's your limit. It's that simple. And I like to call these easy limits because it really is easy. If you know how to plug a number into a function, then you can find the limit of both these functions, all right? Well, let's go ahead and work out these examples and see why this works. So the limit of x squared minus 2x as x approaches 3, I'm going to follow this step 1 and plug 3 into this function. So 3 squared is 9 minus 2 times 3, that's 6. This equals 3. I got out a real number, therefore the limit of x squared minus 2x as x approaches 3 equals 3. Okay, what about this example? The limit of, now I have a rational function, right? X plus 5 over x plus 1. I'm plugging 1 into this function because that's what step 1 says to do, plug a into the function. So I'm going to plug in 1. I get 1 plus 5, that's 6, over 1 plus 1, that's 2. And this can be, oh, this is 3 as well. This can be simplified to 3. Okay, so the limit of this rational function as x approaches 1 equals 3. So let's talk about why this is. If we look at this first function, we can hopefully see that this is continuous. It has a domain of all real numbers. Therefore, if we graph this, we can put our pencil down and graph the entire function without picking our pencil up, right? That's kind of how you think of continuity, at least at the calculus and algebra level. So since I can do that, I can approach any x value from both sides, right? I can approach any x value from either side and find the limit of any x value for this function. For this function, it's not continuous. We do have an asymptote because look what happens when I plug in -1 into this function, right? I get 0 in the denominator. Clearly, there's an issue there. I'm going to run into problems, but I'm worried about the limit as x approaches 1, not -1, right? So the idea is I can still approach 1 from both sides. Basically, I can still find an interval around that point where x equals 1. I can find an interval and still approach from both sides some y value, and that y value I'm approaching is 3 in both these cases. So hopefully that makes sense. These, again, easy limits, but we're about to see some examples where it's not so easy and we got to do some other stuff. Alright guys, I'm really sorry. I know this is a little bit awkward, but I'm editing this video right now, and I just realized that somehow the clip that belongs right here is missing. I think I accidentally deleted it. So I'm going to go ahead and remake it right now. So just pretend everything's normal, pretend I'm wearing the same shirt, pretend I don't have a fresh haircut, alright? Let's go ahead and do this. So, what happens when we don't have an easy limit, alright? So remember, we can plug in our number, we get out a real number, that's the limit. But what happens if when we plug in our number, our function is undefined at that number, right? What if the function is not defined at a? Well, I broke this down into 2 cases. Case 1 is this 0 over 0 case, and we can go ahead and look at this example to see what I mean by that, okay? So the first thing we always do, again, if I want to find this limit, first thing I always do, plug 2 into my function. So when I do that, I get 2 squared, that's 4, plus 2 minus 6 over 2 minus 2. So this comes out to be what? 4 plus 2, that's 6, minus 6, that's 0 over 0. All right, so this is what I mean by that 0 over 0 case. So what does it mean when I plug in a number and get 0 over 0? What does that mean? Well, if we remember all the way back to algebra, I know since you're in calculus, I know you thought you're done with algebra. Actually, you need algebra more than ever for a calculus class. So we got to go all the way back to algebra. Remember what the 0 over 0 means. That means the graph of this function has a hole where x equals 2, right? And we saw with one of our first examples, the graph of a function with a hole, the limit still exists. We can still approach from both sides even though the function is not defined at that single point. So what is the limit? Well, it's the y value that goes with that hole, right? It's the y coordinate of the hole. So how can we find that? Well, what we have to do is find some way to reduce this, find some way to cancel something so we can get this function to the point where we can plug in 2 into that function. And since we have a polynomial over a polynomial, usually what you'll end up doing is factoring. So let's go ahead and try that real quick. So I'm looking for 2 numbers that multiply together to be -6 and add together to be +1. So let's see, what are those going to be? I have x plus 3 and x minus 2. So that's my numerator when it's factored, x plus 3, x minus 2. And then in the bottom, I still have that x minus 2. So now you can see that I can cancel a common factor here, right, of x minus 2 in the top and bottom. So this leaves me with x plus 3. So again, remembering a little bit back to algebra, the only difference between these 2 functions, the only difference is that This function doesn't have that hole where x equals 2, and this one does. But if you graph them, they will be the same linear, right? The same line on top of each other. Again, the only difference is that this one has a hole, this one doesn't. So since this function, the graph of it is basically the graph of this function just with that hole filled in, I can plug 2 into this function, and that's going to be my L. That's going to be the limit I'm looking for, right? Again, I'm looking for the y coordinate of that hole. I can get that by just plugging 2 into this function. So 2 plus 3 equals 5. Therefore, my limit is 5. So hopefully this makes sense. When you have that 0 over 0 case, there's going to be some kind of simplifying you can do, whether it's factoring, distributing, common denominators, and you're going to be able to fix it in some way. Sometimes you got to use the conjugate. Remember back to algebra for the conjugate if you have square roots involved. But you're going to be able to do something to simplify it to where you are going to be able to eventually plug that number in and find that limit and find the number that x is approaching. So hopefully that makes sense. Let's go ahead and move on to case 2. All right, so case 2 is when we plug in this number a, right, this number that x is approaching. We plug that into the function and we get z over 0, where z is any non-zero number. So remember, case 1, 0 over 0, that means there's a hole. Case 2, any number other than 0 over 0, that means there's an asymptote. So we treat these differently, which was why I broke it up into case 1, case 2, okay? So what do we do when there's an asymptote? Well, let's look at this example and see if we can figure it out. And again, we already saw this earlier. We approached 1 and it was an easy limit, but now it's more difficult, right? Because we're approaching an asymptote. But let's go ahead and plug -1 into the function. The first thing we always do when we're finding a limit. So when I plug -1, I'll do this off to the side here. I get -1 plus 5, that is 4 in the numerator, over 0, right? So I get a non-zero number over 0, which tells me that there's an asymptote at x equals -1. So what do? Well, this is going to bring us to this idea of infinite limits, okay? So let's go ahead and look at what can happen around an asymptote. So I'm going to break it up into 4 main cases, all right? This first case is that my y values increase from both sides. This second case is that my y values decrease from both sides, so something like this. And again, that dotted line is the asymptote, right? My third case is that my y values increase from the left and decrease from the right. And my fourth case is that same thing, just flipped, right? That fourth case is, let's see, decrease from the left and increase from the right. So what does this mean, and why does this bring us to this idea of infinite limits? Well, let's think back to our definition of a limit. So as x approaches this value a, my y values have to be approaching some value L, right? That has to happen if this limit exists. Does that happen in any of these cases? In this case, as x gets closer and closer to a, remember a is our vertical asymptote, my y values just increase without bound, right? So since they're not approaching an actual number, because they're just increasing, we say that the limit doesn't exist, but we have an infinite limit of positive infinity, all right? For this case, as x gets closer and closer to a from both sides, my y values are decreasing and decreasing without bound, right? Get closer, decrease, closer, decrease. So we say that this has an infinite limit of negative infinity, okay? And with these, it increases from the left, decreases from the right. So both of these we would just flat out say does not exist. So the limit does not exist, and we don't need to specify infinity or negative infinity. That's what we're really doing in this case. We're still saying that the limit doesn't exist because it doesn't exist in any of these cases, which makes this a little bit tricky. The limit still doesn't exist, but we're specifying that, okay, well, as x gets closer to a from either side, my y values increase without bound or decrease without bound. If we can specify, then we do, and we say the limit is infinity or negative infinity. If we can't specify, then we just say does not exist. So both these cases would be does not exist. And again, this is a little bit tricky. It may be taught a little differently depending on the instructor you're taking. This is just the way I was taught. I referenced a couple textbooks as well, and this lines up with what the textbooks had to say. So just remember that around an asymptote, that's when we're going to potentially have an infinite limit. So there are really 3 options. There's only 3 possibilities for my answer when I'm approaching some asymptote, is either the limit does not exist, infinity, or negative infinity. So how do we find out which of these 3 possibilities we have here? Well, I can make a little chart and I can test some values, right? I can plug in some values approaching -1 from the left and test some values approaching -1 from the right and see what's happening to my y values, right? So that's really the way you'll do this. And again, depending on the instructor, maybe you'll just write does not exist. But most instructors I know, if you just write does not exist and it turns out it's infinity, you'll be marked wrong. So be careful, check with your instructor. So let's go ahead and test some values and see if we can find the limit of this function. Alright, so I plugged in some numbers to see what's happening as x approaches -1 from the left and from the right. And I kind of put them in this table, but I'm also going to do a really rough sketch of the graph. You can use whatever method you want. You do need to find out what's happening around this asymptote, but use whatever method you're comfortable with. I'm going to show you two different ways of looking at it right here. So as x approaches -1 from the left, what happens to our y values? -7, -39, our y's are decreasing. They're getting smaller. So from the left, y's are decreasing. What's happening from the right? So again, I'm going this way. So it's kind of hard to look at it from the table. That's why I thought I'd also go to the graph, because we're going this way. So from 9 to 41, we're increasing, right? So from the right, we're doing something like this, which means what? The limit does not exist, and that's that.
If the limit never approaches anything, the limit does not exist. The limit does not exist!
Okay, so hopefully this helped. Hopefully it made sense. We're going to do a few more examples to finish off the video, but this idea of infinite limits, it's pretty tricky. So it's hard to talk about, it's hard to explain. I did the best I could. Hopefully it helps. Alright, we're going to finish off this video with a few examples. I'll go ahead and work through these step by step. So with this first example, what's the first step? What's the first thing we do to find this limit? Plug the number in. Alright, I'm going to plug 5 into this function. I get 5 minus 5, that's 0. So I get 0 in the numerator. And I get 5 squared, that's 25, minus 25, that's 0 in the denominator. So this is that 0 over 0 case, which means the graph of this function has a hole where x equals 5. Which means what? I need to try to reduce this to cancel something, to simplify, so I can get to where I can plug 5 in, right? Since we have this polynomial over a polynomial and it's already perfectly set up like this, it's clear we're going to factor. Hopefully that's clear. And hopefully it jumps out at you that this denominator is a nice difference of squares and that it can easily be factored. So if that doesn't, you just need a little bit more practice. It's okay, but hopefully that jumped out at you that, hey, wait, that's a difference of squares. And when I factor this, right, we'll see what we get. It's going to nicely cancel. When I factor this, it becomes x minus 5 times x plus 5 in the denominator. So now what happens? I can cross out this x minus 5 with this x minus 5. Those are both gone. This is 1 over x plus 5. So the graph of this function is the same as the graph of this function, except for what? This function has a hole, this one doesn't. So the graph of this function is like this one, just with that hole filled in. So we can plug 5 into this function, right? Into our new function, we can plug 5 in, and that's going to give us the y value for our hole, which is our limit. So I'm going to plug 5 in. I get 1 over 5 plus 5. That gives me 1 over 10. So I'm going to put 1 over 10 here for my limit. And I want to go ahead and write here what was the key to this problem. The key to this problem, to simplify it, was factoring. So I'm going to put factor. Because we're going to see that each of these 3 problems, you do something slightly different to get the limit, to get to the answer. Okay? So we're going to make note of what those things are. So for this second example, same thing. Plug 1 into the function. That's the first thing we always do. So when I do that, I get 1 over 1. That's just 1. Minus 1 in the numerator. In the denominator, I get 1 minus 1. So this is another 0 over 0 case. So I need to find some way to simplify this and cancel something so I can plug 1 in and find my limit. So how can I do that? Well, I think what I need to do, since this isn't a polynomial over a polynomial, right? I think what I'm going to do to make my life easier is combine those 2 terms in the numerator. I think that'll help me a lot to simplify and see if I can cancel something. So to do that, I need a common denominator, because that 1 there, I could rewrite as 1 over 1, okay? So if I rewrite this as 1 over 1, then it's clear that I can multiply that by x over x to get a common denominator, so I can combine those terms in the numerator and see if that helps me out to somehow cancel something, right? So if I do that, multiply by x over x, right, then I'm left with 1 over x minus x over x, all in the numerator. In the denominator, I still have x minus 1, okay? So now when I combine this, I get 1 minus x over x over x minus 1. And since I have a fraction over a fraction, I like to write them both as fractions. So x minus 1 over 1. Because now what I can do is flip the bottom and multiply, right? Fraction divided by a fraction, flip the bottom, bring it up, multiply across. So instead of just combining from here, I'm going to notice that I have 1 minus x in this numerator and x minus 1 in this denominator. Wouldn't it be nice if I could cancel those? They're not quite the same, but they're almost the same. And there's a little trick, there's a thing I can do to make it to where I can cancel them, right? And what I can do is factor out a -1 from either of them, really. I'm going to choose this one, right? Because look what happens when I factor out a -1. So if I take a -1 out in front and I write x minus 1, look what happens when I put the -1 back in. It becomes minus x, which I have there, plus 1, which I have there, right? Same thing as what's here. I just factored out a -1. So if I have this over x times, remember this is times, 1 over x minus 1. Now my x minus 1's cancel, and I'm just left with that -1 factor out in front. -1 times 1 is -1, and I still have x in the bottom. So -1 over x, now I can plug my 1 in, right? I was able to cancel, so now I can plug my 1 in. If I plug 1 in, I get -1 over 1. That's just -1, so my limit is -1. So what was the key to this problem? What should we call it? I know we did quite a few things. I'm going to call it common denominator. Common denominator. I just want to make sure we note the different things we may have to do to find these limits. So factor is one of them. Find a common denominator that could help you out. And now let's go ahead and look at this third example. Let me erase a little bit. All right, for this last example, the first thing I'm going to do is plug 9 in. Square root of 9 is 3. 3 minus 3 is 0. 9 minus 9 is 0. This is 0 over 0. I don't think I have to write that out. I think I can probably see that by now. 0 over 0 case. So I'm going to have to cancel something somehow and get this to where I can plug 9 in and get a value. But I don't really know how. It's not a polynomial over a polynomial. There's no fractions. But there's one thing I can remember that I learned all the way back, again, in algebra. We're going back to algebra, and that's something called the conjugate. What if I multiply the top and bottom, the numerator and denominator, by the conjugate? So the conjugate, again, I keep both these terms the same, and I just change the sign in between. So what if I multiply this by the square root of x plus 3 over the square root of x plus 3? All right, let's see what this does. So the reason I do this is because look what happens when I FOIL this out. It becomes square root of x times square root of x. That's just x. And then I get 3 square root of x. That's plus 3 square root of x minus 3 square root of x. So those middle terms cancel out, right? I could write them out. I feel like y'all see that those cancel out, though. Minus 9. So I get just x minus 9 in the top. And now let's see what happens in the bottom. I think I can go ahead and keep the bottom in this form because look what happens. This bottom is x minus 9 times square root of x plus 3. I now have an x minus 9 up in my numerator. So you could distribute this, like FOIL it out, but what you want to end up doing after that is factoring this x minus 9 back out because that's what we're going to cancel. So we can just leave it here, and I'm even going to do this and reach all the way over here, right? So what I'm really left with after this is 1 over square root of x plus 3. Hopefully y'all followed that. So 1 over square root of x plus 3. Now I can plug in 9, and I get square root of 9, that's 3 plus 3. So I get 1 over 6. So my limit is 1 over 6. And what's the key to this one? I'm going to write conjugate, okay? Conjugate. So hopefully that made sense. I know you got to remember a lot of stuff from algebra, but we have conjugate, common denominator, and factor. All right, so these are just 3 examples. There are probably more things. There are more techniques you have to use to find limits. These are the 3 probably most common things you'll see come up, so that's why I thought I'd put them as examples. But this is a long video. Sorry, guys. Sorry it was so long, but I got more videos to come. Lots more examples. Limits at infinity, derivatives eventually, a bunch of cool stuff. So make sure to, again, subscribe if that's what you want to see. Leave any comments below, hit the like button if you enjoyed, and most importantly, keep flexing those brain muscles. See y'all in the next video.